Okay, so with alternating series comes the alternating series estimation theorem. Okay, so given an alternating series, all right, so let's say I'm going to put indices on this. Right now, if this series passes the hypothesis, these, let's use an abbreviation, alternating series test then the sum, and I'm going to phrase it like this, S minus S sub capital N, the difference between them is going to be bounded by A sub capital N plus 1, right now. This is what's known as the alternating series estimation theorem. Okay. And another way to kind of look at this, so I'm looking at the infinite sum minus the sum that gets cut off. So the sum, in which equals 1 to infinity of negative 1 to the n, a sub n, minus the sum n which equals 1 to infinity, capital N, sorry. It's got to cut off at capital N. Now, negative 1 to the n, a sub n, has to be bounded by a sub capital N plus 1. So the difference between the infinite series and a series that you cut off, what is it bounded by? It's just bounded by the next term of the infinite series. Okay? So this is one way that we can calculate things to certain accuracies. Okay? Because we know that the difference between the infinite sum and the finite sum is bounded by the next term of that sum. Okay, so let's see how we can use this in a practical way to calculate something to a certain degree of accuracy. Okay, so cosine of 1 is equal to the sum n which equals 0 to infinity of negative 1 to the n divided by 2n factorial. Okay? All right. And now the problem states that can we calculate cosine of 1 to, let's say, accurate to 4 decimal places? I'll address your questions in a second. I'm still filming right now. All right, so let's say you want to calculate cosine of 1 accurate to, say, 4 decimal spots. Okay? How many terms are needed? That becomes the question. Okay? Now to do this, what we need to do is we're going to have to find the first a sub capital N plus 1, which is going to be less than 0.1, 2, 3, 4, and 5. Okay? Now, the number of decimal places that you want to calculate this accurate to, that's how many zeros you're going to put on that thing. Okay? And why is there a 5 at the end? Well, okay, that's for rounding purposes. Okay? So it's just kind of a general rule that you would want it accurate to that amount. Could you have it being less than 0.00000006? No? Yeah, but it kind of screws with the rounding. So we have to ask ourselves the question of, in this infinite series right here, cosine of 1, so what does this thing look like? This is equal to now 1 minus 1 divided by 2 factorial plus 1 divided by 4 factorial minus, and that's going to go on forever. All right. So which one of these terms is going to give us an accuracy to 4 decimal spots? Well, it turns out that 1 divided by 8 factorial, and you got to remember that these are factorial, so this is 1 divided by 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. That actually equals 0.0000248. So this is going to be the first term in this infinite series that is going to be less than 0.00005. Okay? So, and remember that this is capital N plus 1. Okay? So, we're not going to actually need this term. So, okay. This means that cosine of 1 minus 1 minus 1 divided by 2 factorial plus 1 divided by 4 factorial minus 1 divided by 6 factorial. Okay? This has to be bounded by 1 divided by 8 factorial. Okay? Now let's see what this actually, let's actually check and see what is the actual difference between these. And so, cosine of 1 minus 1 divided by 1 over 2 factorial plus 1 divided by 4 factorial minus 1 divided by 6 factorial, okay, that actually equals 0.0000 and 245. So the difference between those really, I mean, it is less than 1 divided by 8 factorial. And so you can see that when trying to calculate cosine of 1, man, you only need 4 terms. This calculates cosine of 1 accurate to 4 decimal spots, and that's all you have to do right there. So this, and this one itself, we'll talk about this later on, but if we do the ratio test on this cosine of 1, it is absolutely convergent, okay? And things that are absolutely convergent, they calculate to a certain degree of accuracy pretty quickly, okay? Conditionally convergent series, they actually will calculate things very slowly, but they will, okay? So if you imagine some type of estimate like this, and we did like the Maclaurin series for the natural log of 1 plus x, or something like that, which ends up being conditionally convergent, it calculates it very slowly. We'll do that in another video.